Hello everybody. My name is Thomas Steinmaurer. I'm using Firebird since 2000 when it was born. Also interface in the early days, interface 4.2 I think, so I'm using the interface Firebird technology for quite a while now. What I'm talking about here is a data warehousing environment using Firebird as relational backend. All you will hear in this session is basically based on 2 customer projects we have been building with Firebird using an open source technology stack for data warehousing. Let's start with the agenda. A bit of historical thing, a bit of motivation. The second point will be for those of you which are new to data warehousing, just a bit of an introduction. The third point is we go through a case study I've prepared for this session. We will see how far we go with the case study in respect to time we have for discussing aggregate tables, something very important for a data warehousing environment, and well, in question answers. If you have any questions during the session, just raise your hand and ask here. So first of all, who is familiar with data warehousing, online analytical processing environment? So that's a good start, because the slides here, and so we don't have to skip the slides here. Well, basically, what we do in our business is to, this one here is in German, but I think it's all about that we have some questions on our data, on our databases, or on our applications. So basically, we want to know something. Usually, especially if you deal with rather large systems or rather large transactional systems, usually you get something back like that. So it's not always that easy just to get the right information from the data out. So looking back a bit in history in respect to processing data and data management, back in history we had classical reporting systems. We also had so-called decision support systems which should support experts to create the right decisions in time. And we also have execute information systems. So they are still in business, but the things changed a bit in respect to managing data, in respect to making decision out of data. So what we have today is so-called data warehousing. Basically, it's a centralized data storage for enterprise-wide data analysis, so reporting, ad-hoc analysis, data mining. So the basic idea of a data warehouse is to have, in respect to data, a single version of truth. So usually you have data across your enterprise in different departments, and all of them are running any reports, are starting Microsoft Excel, connecting to a database, doing their own stuff in respect to analysis and reporting. So the basic idea, or the great advantage of having a data warehouse is to have, in respect to data which you have to analysis, is you have one single database, one single version of truth in respect to your business data. And there is a concept to the ETL tools for extracting, loading and transferring and loading, is just to extract data from your different operational sources. This isn't limited to relational backends, for instance, but also to content management systems. So any data you store in your enterprise must be extracted and transferred and loaded into our data warehouse. And a concept based on data warehousing is, or a method is, online analytical processing. So this one is based on a multidimensional model. We will talk about it a bit later. And standard operations like slice, drill down, drill up for ad hoc analysis. We will see in the case study a real-world example, a web-based example on how this could look like. So let's talk a bit about data warehousing. So why do we need a data warehouse? Well, as said, all information is in one place. We have the most important thing is for data warehousing, you have up-to-date information. So if you're in the business to make decisions out of your data, you must need up-to-date information. Quick access is another one, is another requirement. No size limits in respect to any physical limits you have with disk drives or something like that. Very important is that you have the history available of your data, so you can look back how sales looked like 1 year ago or a quarter ago. It must be easy to understand, especially for the end users. So the end users shouldn't have any knowledge about that data warehousing is operating in behind the scenes. So that's an important requirement as well. Well, that's all a nice bullet. The nice bullet list. The thing is that data warehousing is another concept you can learn. So all of that is is achievable in respect if the data warehouse is designed and built properly. So Bill Inman is the godfather of data warehousing. So he had 4 requirements here. It should be subject oriented. So especially if we are talking about sales data, then you must have all entities and events related to example sales data linked together. All changes to the data are tracked to enable reporting that shows changes over time. As said, for instance, how did the sales data changed over time, for example. Data is stored and never overwritten or deleted. This is pretty much a requirement for a second thing here. And integrated. Integrated means that all operational sources, all transactional databases are integrated in one repository. So I don't know how your business look like, but if you deal with rather large transactional systems, you are probably in such a business with a lot of tables linked together. A lot of users are connecting to the system, inserting data, updating data, and probably for your analysis tasks, you just need a few of them, especially if we are talking about a sales department. They aren't interested in stuff like, I don't know, manufacturing or something like that. So usually we deal with rather complex transactional systems, and in respect to our analysis task, the data model or the use tables or the use data might be a reduced view of your transactional business. So a transactional system compared to an analysis system differs in a few aspects. So transactional system, usually operational users are working with this system. We have it's the classical daily business, transaction processing, entering data via our application or something like that. The database design is application oriented, so just normal relational modeling, what you're used to. We have only up-to-date information, so regularly, usually no historical data. No historical data. Data is atomic, normalized, and isolated. Access is rather characterized by short-running transaction, both read and write, and the system requirements usually is transaction throughput. So that are things usually we have in a transactional system. On the other side, the analysis system is usually analysis or manager or executive persons usually use such a system. We have decision support and analysis, so it's not that kind of daily business we are used to. It's subject oriented, so in coming back to the sales example, for salespeople, for instance. And we also have historical data, very important aggregated data, so classical aggregate function like minimum, maximum, average, sum, count, or something like that. It's usually not we use a multidimensional model here just to, we'll see example later on that, and integrated. So integrated means enterprise-wide data warehousing, consolidating different aspects of your enterprise, of different departments. Access is usually basically reading, so no write operations from an end-user perspective, and rather complex queries. And the number one goal here is just a query throughput. So basically a data warehousing environment is measured by user acceptance in respect to how fast do I get my information out there, if asking for queries like how did the sales look like for the last quarter, aggregated to an average value, for instance. So these are the difference. We also have a different here in respect to our database business. First of all, a transactional database is usually 24 every day. So we have a high number of concurrent database connections. Usually there is less memory for caching required because of mainly write operations, and usually there's little reorganization necessary, creating new indexes or something like that. On the other side, an analytical database possibly used just in-house, so you don't have, possibly not that strict requirement being online every time. You usually also have a smaller number of concurrent database connections, so more memory possibly is reasonable for caching, and based on concrete query patterns, so queries which users execute. There might be more reorganization necessary, for instance, creating another aggregate table for this particular query because it is called 10 times today or something like that. So for our Firebird knowledge, this is interesting list because in respect to caching, possibly what architecture we should use for a transactional system and an analytical system. So this is how a generic data warehousing architecture looked like. You have your source systems here, which are unlimited to databases. This could also be files, an ERP system, a content management system, whatever. So you have different sources of your data in your enterprise. What we have now here is an ETL process, which basically extracts data from your sources here, transforms, and loads it into your analytical database in your data warehouse. On that data, you build different cubes here. So cubes possibly for every department or whatever your query look like. And at the end user side, you have different applications here. For instance, any charting or dashboards or any office product or a generated report. So that's a pretty generic data warehousing architecture, and we will see later on in the session how we implemented that architecture in 2 customer projects using Firebird as a relational backend. So that's pretty much what I've said already. Again, the important thing is that the data warehouse, so the data storage of the data warehouse is the single source of truth. So it's getting pretty hard if you have again different data warehousing or different cubes in your company. So that's really an important thing to have the single source of truth in respect of your data for analysis tasks. The multidimensional data model is not that hard to understand. We have basically we have a cube not limited to 3 dimensions, for instance. You could have more dimensions. So we have measures. is pretty much just a scalar value, which tells us, for instance, book of type Thriller has been sold 40-50 times in 2006 for a particular state. So that's really a measure in a data warehousing environment in a cube, which gives you real facts about your data. And there can be different dimensions. So in our example here, it's just a product or a time is very, very common for data warehousing or customers or whatever. So based on the storage, how the cube is stored internally, there are 3 different storage formats available. The multidimensional OLAP, it has a really proprietary multidimensional format for storing data on the disk. And an open source example is, for instance, Palo. Another one, a very common used, especially in the open source world, is the relational OLAP, which basically stores your data warehousing data again in a relational database. One example of such an OLAP server is, for instance, Mondrian. We are using in our customer project as well. And well, there's a mix of both worlds, but that's especially in the open source world not really used. I think Microsoft SQL Server allows to have a hybrid OLAP as well. So, but we are using the relational OLAP model in our example. Well, it's in a relational OLAP, it's all about relational modeling again. So pretty much the knowledge we have already when modeling a relational database can be directly applied to modeling a data warehouse. So for instance, we have several dimension tables here. For instance, this one is date, so year, quarter, month. We have a device. We will see the case study is not based on sales data. Usually data warehousing is used for sales data, but we are using that a bit differently. We'll see that later on. We have other dimension tables like the operation minute, the operation hour, because we are talking in the case study about devices, for instance, in sensor networks which deliver measurement values. So the operation hour of such a device or electronic vehicle or something like that might be interesting for our analysis tasks, as we are using our system worldwide. So our vehicles can be around the world. We also have to deal with time zones, so and more. So basically, our data, our fact data, or is also called fact table, is here. So we have the all dimensions with foreign key constraints linked together to this one fact table. We have different value types. For instance, is the value of type current, is the value of type voltage, is the value of type temperature, and the last thing is really the scalar value, the measured value of this particular vehicle. So this is called a star or snowflake schema. You usually tend with these terms if you're modeling data warehouse in the relational world. So what you see with the green boxes here, if we only would have the fact table here and the green boxes here, we would talk about the star schema because it's oriented like a star. If there are some dimension tables also linked to another table, then we are talking about the snowflake schema here. So while we are used to SQL to query a relational database, querying OLAP cubes is done by another language which is similar to SQL. It's called Multidimensional Expression, MDX. I think it has been invented by Microsoft, as far as I know. So another concept here is XML for analysis. It's basically, extends the MDX language with XML tags, so it can be executed over HTTP using SOAP methods. And this is just a very simple example how an MDX query could look like. It's a bit familiar, but one needs to get used to such queries because you have to think about columns, rows, dimensions. So it's it's a bit different, but it's similar. So, well, standard operations is slice, dice, drill down. So all what you have in respect to the end user, if he is querying or executing ad hoc queries, slice is apply conditions to look at only parts of the cube. So if you're only interested to one dimension, for instance, I'm only interested in how many products have been sold to a particular state, and it's usually a slice operation on a cube which has more dimensions. Dice is pretty much swapping the columns and the rows if you want to swap the visualization. Drill down is which allows you to navigate down to more detailed data. For instance, if you start with an average value for the entire year and you want to know how did the value look like for the quarters, then it's usually a drill down operation you're executing. Drill through is pretty much the same than drill down, and roll up is going back upwards if you have been on a more fine-grained data. So basically that's a very, very fast introduction to data warehousing. Now let's have a look on our case study. Well, I've already mentioned that usually data warehousing is still closely related to sales data. But what we have seen in our company, and we are involved now for some years now, building data warehousing applications for the manufacturing domain, especially for industrial processes or something like that, this area, not only sales data, but also in industrial manufacturing domain is interested in applying data warehousing concepts in their enterprises. So, for instance, sensor networks, like having electronical vehicles driving around. So e-mobility is just, I don't think just a buzzword, but real. I think e-vehicles are coming along. So to measure, for instance, how the rechargeable batteries are doing or something like that. So basically we have to deal with sensor networks pretty soon in the data warehousing environment. So what I call a sensor here is pretty much anything which produces any kind of measure value. It can be a chip, a battery cell, a programmable controller, something like that. So measured values can be voltage, current, temperature, whatever you collect from these sensors. So how does that look like? We collect data from sensors in the field out there. We store them in a transactional database. So we have a split between our transactional system and our analysis system. We extract, transform, and load the data into our analytical database. And what we do is we provide a web-based multidimensional ad hoc analysis query environment. We had been implemented quite some data warehousing projects now with Microsoft SQL Server. The two customers here wanted to have especially the databases on a Linux server, so we have been other options as well, and with Firebird, which I'm using quite a while now, we finally got around the open source topic, because their server application was entirely built with open source software. So the analytical software architecture looks like that. We have our transactional database with a table called data record, which usually pretty much stores the measure value out of the field. Then we have an ETL job using Cattle or Pen2 data integration for extracting the data here, transforming, and loading it into our analytical database. Our analytical database consists of a few dimension tables, a fact table, and in our example, I've built one aggregate table to speed up very common query scenarios. So the ETL job pretty much looks that way. It's we go a bit deeper later on. So it has a starting point, and data comes in. The different dimension tables get loaded or updated, and the last thing is just to insert the data from our transactional database in our fact table here in our analytical database. So that's just a few of a visual environment. You can build up your ETL process with different transformation steps. So that's a very powerful and a very good product for such ETL jobs. On the client side, we then have an Mondrian Depend2 analysis services, the open source OLAP server interacting with our relational analytical database. And on the front end side, we have chosen OpenEye, which is an web-based application using the XML protocol to interact with the analysis services. Well, there could be, of course, other client applications as well, like the Cube Designer, a regular SQL tool to access our relational database. The used software technologies here was GDK 6 with Firebird 2.1. We have converted one project to 2.5 without any problems. So GBird in its current version 2.1.6 in our case works fine with Firebird 2.5 as well. So then we had for the ETL part Depend2 data integration, also formerly known as CATL. Then we have as OLAP server Mondrian, OpenEye, and for the database development stuff, not IB Expert, but Database Workbench. So for this part here, this was the only commercial tool we have used. The other tools here, the other tool set here is open source. Well, the physical data model of our transactional system is pretty much we have one data record table which basically stores all received measured value from the field, and regular relational modeling business with the device type. Is it a vehicle? Is it a chip or something like that? The particular device. Well, a device is related to a customer. We want to analyze things per region. A region can be a continent. A region can be a country, a state, down to cities, for instance. Yeah, different value types, temperatures, voltage, as I've already said. So that's pretty much the relational model for our transactional database. The analytical database looks a bit more complex. I've told you that at the beginning, usually the transactional model is more complex. But in this scenario, we have a bit few more relations in our analytical database. We have seen that before already. So the so-called fact table here is the key point in our relational analytical model here, storing the measurement value from our transactional system. So live demonstration. Yeah, just a few pictures in case something bad happens with my online presentation. Well, let's give it a try. So, well, it's two Firebird databases with pretty much the model we have seen here already. So what we have here now is, let's say, we want to have a look on the ETL job. There is a visual front end which allows you to model the ETL job and its transformations and steps in a visual environment. So For instance, it looks like that. This is a transformation. This all is one ETL job. What you see here is this is one transformation which basically loads one dimension table. We are using a rather simple way to detect if something new, if a new record in the unit table in our transactional system has been added by executing a max of the primary key value. So with this concept, we are using a more complex in the customer projects, but for this presentation, we are just looking if any new records have been added in our transactional table unit. And then we are basically executing a SQL statement on our transactional database. This goes through a field mapping. The field mapping on the left-hand side, the field names is from our transactional system, and the field names here is from our analytical system. So that's pretty much the table output step here is just configuring some things like the connection, the target table, and the field mapping ensures that data from our transactional system from the fields go into the right fields on the analytical system. So that's a very, very simple transformation for loading the unit dimension table in our analytical system. It's pretty much the same for the other dimension tables, region, type, region, device type, and so on. With this transformation here, we are loading the fact table. It's pretty much the same, like detecting new records in our transactional system and basically then inserting into our fact table here. When you are in ETL business, it's usually one question is how often should the ETL job run to process new data and to insert new data into your analysis system. Well, you could run the job in batch mode, which more or less gives you for a particular time frame up-to-date data in your analysis system. What we have done here is using Firebird event, the Firebird event technology. So what we have done is to build our own transformation here. So we have implemented a Java file or Java project, which basically encapsulates the event technology of the Jaybird driver. So what we have here now is just a few things like job entry name we want to connect to our transactional database and how the event name looks like. So whenever so we start the ETL job, it's running in the background, waiting for a new event happening, and the event which happens is basically in our transactional system that we have a trigger on our data record table. So every time a new record gets inserted into the transactional database in our data record table, event is posted and the ETL job receives these events and kicks in. So what we have reached with this implementation here is that we get near real-time ETL loading with this approach. So that was one major requirement from our customers to have basically near real-time up-to-date information on an analysis database. As said, this transformation step here isn't part of the Pentaho environment, but it offers interfaces, and so you can easily extend the Pentaho environment with your own transformation steps. So this is the route what we did here. Well, so let's see. The job file is just a regular file. So if we go into this one here, and this is our job file. It's pretty much XML. What's coming out if you're modeling your job, your transformation in the visual environment. So what we then have here is a batch file. The batch file sets a few environment variables and calling a batch file from the Pentaho environment are starting the job file. So if we are running this one here, we will see that by using the event technology of Firebird, we are now in some kind of idle mode. So whenever something gets inserted into our transactional system here, let's say I've prepared a stored procedure which just inserts a few data. So it's not committed yet, but if we commit this one and we are fast, we will see that the ETL job jumps in. So basically, what we have here now is we have with the stored procedure, we have inserted some data in our data record table of our transactional database, and with the ETL job, we transfer the data into our analysis world. So if we do a count table here, we have pretty much the same record count here. So what we have here now is we have the entire data in our analytical system, analytical database. What we now need is our web-based front end. So we are using OpenMy. OpenMy is pretty interesting implementation for an OLAP client, in my opinion. It can interact with an OLAP server with the XML-A protocol, with the standard protocol. So it's usually a web application running with Apache. So let's see if okay, we start the web browser here. And we say localhost. So OpenMy is just a regular web application with authentication. This was one important requirement of our customers as well. Because Mondrian, the PAN2 analysis services, comes with a very simple web-based front end as well, but you don't have user authentication. You can't save any queries, any ad hoc queries into the file system for later reuse and something like that. So OpenMy provides all that. So if we connect in here, what we see here now is I have prepared two queries. So pretty much if I click on this one here, I have the dimension date. So we are interested in values in respect to year, quarter, and something like that. All devices which are out there, and we are have the average measured value along all devices for all dates. So what the front end supports here now is to just navigate down to, for instance, I'm interested only in the average value for a particular quarter, down to a particular month, down to a particular day, for instance. So that's the nature of a data warehousing system, to have a very flexible way to query data stored in an analysis system, in a data warehousing system, with aggregates. Average was just an example, or I could simply go up here and drill up again, or I'm interested only in, I can hide the empty rows. So I'm, for instance, only interested for a particular device, for instance, so, or device type and a particular device. So I'm able to pretty much navigate through my cube, my multidimensional model, in a very user-friendly way. I can customize the things here. For instance, I'm also interested in the value type, because it doesn't make much sense to have an average value across voltage, temperature, something like that. We also can drag and drop the value type dimension here and see how did the different average measure value looked like for the current, for the temperature, for the voltage. So it's just drag and dropping around a new dimension here, or if I'm totally, I don't need the device information, so just the average value over for a particular quarter, then I'm pretty much here as well. I can have, depending on how I've modeled the analytical model, I can also see, okay, how did the minimum value look like, the maximum value. So that's pretty common also from the SQL world with the aggregate functions available here. Yeah, well, with particular with OpenEye, you could save the current view, the current query into the file system, because for instance the MDX statement would look like that for this particular example. So that's very useful and very convenient for the analysis guys for reuse different queries. You also have a user concept here. Well, I'm logged in as the administrator, but you could define regular Apache users, which then only have their own reports, for instance. So that's pretty nice. You could also have a chart. You could export to PDF, Excel, something like that. So, in my opinion, in the open source world, OpenEye is pretty flexible beside the Pentaho, the entire Pentaho business intelligence stack. Any questions to the example?
So,
yeah?
How does OpenEye recognize which one are the dimensions and which one is...
Yeah, it's a very good question. So OpenEye is just the front end interacting with an OLAP server. It's a web application, so we have Apache here, web apps, OpenEye. Let's see, forgot now. Sorry, the ESTUB OLAP is the web application. And we have a cube definition file. So a cube definition file is XML. Don't worry about the thing here in the text editor. There's also a visual cube designer available. So what you do here is, for instance, you define a dimension, value type dimension, by providing the table name and what levels do you have. We better see the level thing here. If we are talking about the date dimension, so one level, the upper level is year, then there is the quarter level, month level, day level. Also for the time, hour, minute, second, and so on. So there's one XML file defining the cube with the dimensions, and with the cube itself and the fact tables. So the fact table here is again linked to our physical table with the different dimension usage defined in the text file above. So this is the cube dimension, and Mondrian, so the OLAP server Mondrian, is using this XML file. So it's the cube definition for the OLAP server, and OpenEye interacting with the XML protocol with the OLAP server pretty much knows then which dimensions and so on is available. Well, there are no other questions. Yeah. 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 That's all part of the event support in the different access components. So JBird is handling that behind the scene. Basically, the listening client application gets notified if the transaction gets committed. So let's say there is one transaction and 1,000 records get inserted. You only get one event notification for that. So the ETL job kicks in, processes the newly inserted record in a snapshot isolation transaction, processes this one, commits, and it's done until the next next insertion happens here. In Jaybird, yeah, this. I just wanted to show that something happens behind the scene if executing the. I even have started the ETL job in basic logging mode. So I think basic is pretty much basic. So there are detailed debugging. Well, yeah. Okay. Well, one other thing, we have 5 minutes left. One other thing is aggregate tables. So what we have seen in our example here is that usually you always query aggregated measure values. So with a rather small system or with a rather small number of records in your fact table, you are pretty fine without using aggregate tables. So that's just if although Mondrian provides caching, it's usually a statement is executed if Mondrian hasn't been read the values yet. So we are just in the business of executing on-the-fly aggregate statements, which you can imagine if you have a fact table with in the area of 100 million records. That won't lead to response time, which user, I'm pretty sure, won't accept. So we are pretty much, when talking about user acceptance in a client environment, you have to deal with pre-aggregating data. So, well, aggregate queries are very common to our scenarios here. So you all know that aggregate functions count, sum, average, min, max. So the idea is with aggregate tables to aggregate the data, the result set of aggregate queries in separate physical tables for later reuse. So basically the goal is to minimize the number of page records reads for getting a result set of your aggregate query. Well, and you have to deal with redundancy, because you have the fact table and one or more aggregate tables where you have data to keep in sync, and you also have to build up an update strategy to have your aggregate tables feed reflect the correct data. If you would have to execute the aggregate query on the fly on your fact table. Well, other products like Oracle SQL Server have implementations for that, also called materialized or indexed views. The basic thing here is that even if you have materialized or indexed views, that querying data which is stored in an aggregate table should be transparent for the end user. So the end user should not have any knowledge about if there's an aggregate table or not. So while Oracle SQL Server, for instance, support materialized and indexed views, even if in smaller, not that high-priced editions, the so-called query rewriting engine, which basically transforms the user query to a query on the internal aggregate table, is usually included in the higher priced editions. So this is something you keep in mind. You should have keep in mind if you're reading materialized indexed views are supported by SQL Server or Oracle, for instance. So with Firebird, well, Firebird doesn't have any materialized or indexed views yet. Hopefully they will be included sometimes. But with triggers and stored procedures, we have the right tool set to build our own mechanism here to keep our fact table data with our aggregate table data in sync. So the idea in our implementation was pretty much storing pre-aggregated table data in regular user tables and keep pre-aggregated data with the base tables in sync by using database triggers or stored procedures, whatever update strategy we choose. And there are 3 update strategies available in the literature and also in practice. The one is taking just a snapshot. So every time you execute, for instance, a stored procedure, you delete the entire aggregate table and simply insert the aggregated result set again and again. The eager mechanism is pretty much the most important thing if you really want to have your aggregate tables in sync with the fact table, because there is a trigger on the fact table, and with a delta mechanism implemented in the trigger, you pretty much update your data in the aggregate table. And there is a third one. It's a mix of snapshot and eager. Is the lazy mode, which basically logs any new fact records into a separate table, and processing and reapplying the delta mechanism here is done at a later point. For instance, if you can live with updating the aggregate data every night, for instance, then you could choose the lazy mode, because whatever update strategy you choose here, if you're using the eager mode, then your ETL job will performance will decrease, because there are additional overhead, additional cost because of executing the triggers and processing the delta mechanism. Well, it's just what we have implemented in this case study in the customer projects. We have a few more aggregate tables. It's just another table with pretty much the same links to the dimension tables, except that we don't link to the date dimension directly, but we store the year, quarter, and month pretty much inline the aggregate table. So that's pretty much what you need for an aggregate table along the date dimension. And then there's also an additional table for the lazy mode, which pretty much looks a bit like the fact table, which logs any new records inserted into the fact table into the delta table, which then gets processed and the delta mechanism reapplied. Well, there are different stored procedures for SS stands for snapshot loading. We have one for eager loading, and we have one for lazy loading. One procedure per aggregate table. And we have two triggers on our fact table. This one here is responsible for implementing the eager mode. So it's executing this store procedure here and applying the delta mechanism. And this one here is for storing newly inserted records into our log table. Well, the nice thing about, we have been talking about the query rewriting engine here, that Panther analysis service, Mondrian, has a query rewriting component included. So if we have the right, we have to define the aggregate table in our cube here. So, but this is the only thing from the XML cube file here, what you have to do. So every time a user query gets executed, which involves somehow the date dimension, Panther analysis service is able with that definition here not to go to the fact table but to the aggregate table. So for the end user, it's completely transparent. So the end user doesn't have to know about aggregate tables at all. So that's one very important and powerful feature of Panther analysis services. Live demonstration is, well, the time is over. It's pretty much just showing that in the log file of Mondrian that we see that the aggregate tables are used and not the fact table when issuing queries on the date dimension. So I think we can skip the live demonstration here. So thanks for attention. I've just collected a few links here if you want to go a bit more deeper into the area, especially the aggregate tables. There's an article. I've written an article about that. So if you are interested about the aggregate tables in more detail, then you're welcome to read this article. So thanks. Yeah.
Just a small question. table for the delta, a separate table, and not just reviewing that on the fly?
Requerying, especially we in our projects, we have an estimated data volume in the million area. So if we have to requery things to get things done, I don't know if we would be happy. I don't know. We have chosen the delta route because it's described in the literature as such in the books, and the delta mode is really nice because you have also a history of what happens in respect to keeping the aggregate tables in sync. So you see what have been synchronized and what now. Yeah.
But you have to keep that. You have to like drop it or something like that.
Well, you either you set a processed flag or you delete it from time to time. Because, sure, it will grow as well, yeah. So, there are no any other questions. So, thanks for attending and, enjoy the conference.